Okay, well, good evening. Welcome to part one of the annual beginner's guide to astronomy. Hopefully there'll be something in here, even if you're not a beginner, something new. This isn't the first time I've talked about this. In fact, this presentation's been around in one form or another since about 2003. So it's sort of been updated a little bit, but it's really about visual observing. So I think we've probably talked enough about like how to take photographs of things in the last few months. So this is really just aimed at people who want to get out with a telescope or binoculars, okay, over the next sort of 6 to 9 months. So yeah, the Nastro binocular 75. So despite the name, you can still do this if you haven't got binoculars, okay? It's going to be tough to see all of these with the naked eye, but certainly you'll get something out of this if you've got any kind of telescope. You can still chase down these objects that I'm going to tell you about. As usual, if you've got questions you want to ask, put them in the chat and I'll try to deal with them as I get to them or at the end of the talk. So what this is basically a spreadsheet, okay? So I'm going to talk a lot, but essentially this is a spreadsheet with 75 rows in it. And what I've tried to do is to kind of like choose some interesting deep sky objects that everybody is capable of tracking down and observing, either with binoculars or a telescope. So I'll tell you about the objects themselves shortly. I'll tell you why I came up with the list for a start, because there are plenty of lists in astronomy, plenty of catalogues that you could choose from. What's so good about this one? I'll give you some advice about if you want to take it a bit more seriously and maybe record observations about the things that you see. But mostly this is about practice and enjoyment, okay? If it ever becomes an onerous task to track down these objects, it's not really working, so just abandon it. But you'll see the purpose of this as we go through it. Now, along the way, I want to tell you about some kind of like related concepts. So, for example, things that you probably heard about, like right ascension and declination, basically how we measure position of objects in the sky. Also a little bit about brightness, which is the magnitude of these things. I'll tell you about the different kinds of objects in the list. So you'll find there's a good mixture of star clusters, nebulas, and galaxies in there. Let's make a start on this. Now, I'm not the first person to come up with a list of stuff in the sky, and there are definitely more famous lists around. One of the more famous catalogues are the Messier objects, named after Charles Messier, a French astronomer from the 18th century. Messier was essentially interested in comets, and comets are faint, fuzzy things when you see them through a telescope. And if you're an astronomer, there's a degree of fame attached to them, because if you discover a comet, it carries your name from that point forward. So Messier really was interested in comets and looking for new comets, but he would quite often stumble across these faint fuzzy things in the night sky, which weren't comets, and that really bugged him. So he kept a list of the things that weren't comets. And now, of course, Messier's dead and gone, and it's his list of non-comets that he's mostly remembered for. He did actually discover, I think, 12 comets in his lifetime, but who's heard of them? Well, you guess they're called Comet Messier, but really, what do we know about them? It's his list of objects, M1, M2, all the way up to M110 that people remember this guy for. It says 109 fuzzy objects, and I just described M110. It's because his list wasn't perfect. Like, some of the objects in his list, he gave such vague descriptions for that even today we're not sure which ones he was actually talking about. So some of them are duplicates, and some of them were discovered by other astronomers as well. So he didn't discover like the entire list, but certainly when you're an amateur astronomer and you're looking for things to track down with your telescope, it's usually the Messier objects that you go to first, because these tend to be the brightest things, the things that either were discovered by Messier or were known since antiquity. So there's numerous star clusters, for example, the Pleiades star clusters in there. There's even some nebulas like the Orion Nebula and some bright patches of the Milky Way as well. M24, I think, is just a part of the Milky Way, as well as lots of other things. But there's a thing in amateur astronomy called the Messier Marathon. which is on a particular night of the year. I think it's around about March when it's doable in the Northern Hemisphere, where people will try to visually track down all of the Messier objects in a single night. So it's a bit of a task, but I've never been able to do it because being in Northumberland, not all of the objects are visible from here. So it's a non-starter for me. I can't actually make progress on that. Where's the fun in completing 98 objects out of 110? So I wanted to come up with something that I could actually do from Northumberland. So this is the kind of reason behind the NB75. So I came up with a list of 75 bright objects that are potentially doable from Northumberland. But anyway, the Messier objects, I'm pretty sure everybody has seen at least some of these, but whether you've recognized it as a Messier object, I don't know. The Andromeda Galaxy, M31, people tend to know some of the brighter ones by heart. If you gave me a Messier object number, I would get it. And that's, I mean, most of them are galaxies. So if you want to like play a game where somebody randomly gives you a Messier object, if you say a galaxy, you're probably going to be right, just because the majority of them are. Now, there's another list of objects as well, which has become popular with amateur astronomers in recent years, and it's the Caldwell objects. Now, this was kind of like a list of objects which extended the Messier objects with some brighter ones that for some reason Messier chose not to include in his original catalogue. So they're named after Patrick Caldwell Moore, and there are 110 of them. And Messier was observing from France, and he couldn't actually see far into the southern sky. So Patrick Moore extended the list to include some of the really bright stuff that no doubt Messier would have included had he been able to observe it from France. So it's another list of objects. But again, 40 of them don't get above the horizon in Northumberland. So the Caldwell objects are kind of arranged in order from north to south. And I can get down to about Caldwell 50, something like that in the list. But beyond that, it's kind of like they're inaccessible from Northumberland. But again, there's lots of kind of like famous objects in this catalogue, things like the Rosette Nebula, the ET cluster, the Veil Nebula, lots of things that you probably were shown when Nastro had observing sessions, at Hawksley. And they're either from the Messier catalogue or the Caldwell catalogue. Those two cover basically all of the kind of showpiece objects in the night sky between them. Okay, but they're not the only two lists in astronomy. So other catalogues, for example, you've got the New General Catalogue, which was established by William Herschel and his son John Herschel, and William's sister Caroline. So they contain nearly 8,000 objects, the majority of which are galaxies. That was extended in the 19th century by Dreyer, who came up with the Index Catalogue. So he added another almost 7,000 objects. Then in the 20th century, you've got Melot, who studied star clusters in the Milky Way, adding his own star cluster catalogue. So you've got the Melot clusters. And Colander from Swedish astronomer Per Colander, again, adding lots and lots of open clusters. Now, lots of these catalogues share objects. So, for example, NGC 210 is, I think, the other name for the Andromeda Galaxy. Okay, so you've got lots of overlap between these catalogues. They're not kind of individual lists containing unique objects. I guess if you were making a database, which people do for computer software for this, you've really got to be kind of like checking for duplicates in your final database when you do this sort of stuff. And even like software that I've got, like Sky Tools and Sky Map and so on, there are kind of like when you zoom into areas of the sky, sometimes multiple kind of almost overlapping objects plotted on top of each other because of all the duplicates. So it's a very difficult thing to stay on top of, especially nowadays, because there are upwards of like 100,000 deep sky objects. Quite often, a lot of them are programmed into the handset of your go-to telescope as well. Amateur astronomers have come up with their own lists as well. So the Herschel 400 is a really popular one as well. And I'm just reaching over to my bookshelf. Just a sec. Just there, look at that. It's a really good book as well. Steve O'Meara, who writes a lot of these books, is an author worth tracking down because he discusses how a lot of these things appear through various sized telescopes and binoculars as well. So he's got the Herschel 400 here. He's got one for the Messier and the Caldwell objects, plus another 2 or 3 for like things that aren't even in those as well. So Steve O'Meara, very good on this particular topic that I'm talking about tonight. There you go. As well as having like all the star charts about how to find them as well. So, given that you've got all those lists, what's the point of this one? Well, back in 2003, not long after Nastro started, I was getting a bit frustrated that I couldn't complete. I couldn't get closure on a list. That's desperately sad when I think about it now. But anyway, it kind of inspired me to come up with this. Also, back then, I noticed that whenever we met up as a club, people were always talking about the same objects over and over. Oh, did you see the Andromeda Galaxy last night? Yeah, it was brilliant. What about M13 and Hercules, the Hercules globular cluster? Yeah. And then that would kind of like would roll on to the next meeting, and people were just constantly revisiting. Oh, it's winter. It's the Orion Nebula. Did you see the Orion Nebula? Yeah, after I watched the Orion Nebula, I had another look at M13. It was brilliant. And then M31's getting a bit low, so I had a look at that again, but it was still there. You'd think there were like 3 objects in the sky that you could find in Northumberland instead of there being thousands. It's just that some of the others are kind of like little gems that are unknown to most people before they start astronomy. So it was to provide a little bit of inspiration for people to look beyond kind of like the handful of objects that people usually look for. So I came up with a criteria for deciding whether an object would make the cut for my list. Okay, so all the objects had to be visible from Northumberland at some point in the year. Okay, now the rest of this is just kind of technical stuff about what I mean by visible. So it must get, to above 10 degrees above the horizon. I don't want it to be so that you have to kind of like travel to somewhere where you can't see the Cheviots or you have a completely flat horizon. So they had to get to a decent height above the horizon, and I chose 10 degrees an absolute minimum. They had to be reasonably bright. That means visible with a good pair of binoculars, okay? And I wanted to have a list that contained a kind of good spread of objects, so galaxies, star clusters, nebulas, and other things. When I did that, I then went through them and tried to assign a level of difficulty to each object. So I wanted to have like not just like a spread of different objects, but I wanted to have like a range of difficulties as well. I wanted it to be so that there were a good number of easy objects on there, but then you could move on from that and there'd still be a good set of more challenging stuff. And then beyond that, for the really, the ones who really want to persevere with this, I wanted that to be some really challenging stuff where maybe you would have to make more of an effort. Maybe you'd have to travel to a really dark sky and wait for a certain time of the year to see it. So applying all of those constraints to all of those catalogues that I told you about, I managed to whittle it down to a couple of hundred. So that's still quite a lot. So out of that couple of hundred, it was kind of more subjective. It was the ones that I wanted to include after that. So after I did whittle it down to 75 objects, why my 75? Why not 100? I'm not clear on that in my own head because it was like 17 years ago when I did this. 100 strikes me as being a better number. But anyway, 75, there we go. It's different, I suppose. So there's 39 open clusters. So those are things like the Pleiades. The Pleiades is an open cluster. I'll get into the detail of what these are shortly. 11 globular clusters, 5 bright nebula, 2 dark nebula, 6 galaxies, asterisms and stars. Okay, so I've put some different things on there to what Messier had envisaged when he did his list. So I've actually got some star patterns in there as well. There's one planetary nebula. You might be able to guess that one if you've got any experience of chasing these things down. And the Milky Way is in there as well. The Milky Way is technically the biggest deep sky object in the sky. So there is the Milky Way in there as well. These objects are scattered across the sky. That means you can go out at any time of the year and track down some of these objects. Okay, so you don't have to wait for winter just to make a start on this. Some of these objects are only visible at some times of the year. Some of them are visible all through the year. Okay, so you can make a start at any point in the year on this list. Here's the list. Do I go through this row by row? No. Okay, I've put this on the Nastro website. It's actually been there for about 3 years, sitting in a dark corner of the website. So I'll show you how to get to it at the end of the talk. But there it is. So you might kind of like look down each column and see that I've got an ID from 1 to 75. I've got the popular name. Many of these objects have more than one popular name, but I've put the one that I know, kind of. Because the spreadsheet's downloadable as well, you can sort these into whatever order you want. You can sort them by brightness, magnitude. You can sort them by difficulty. You can kind of like, you know, you can, what's the word? You can select only the easy ones if you want, so that they're visible. So in spreadsheet form, it's a little bit easier to look through this thing, okay? But here it is. Now, because of the way I've got it ordered provisionally, some of these things are visible, for example, at certain times of the year. So January till April, these ones are visible. These are kind of visible throughout the, well, from October to December, it's got on the top there. So January to April, this is the best season to see this group. May to September for this group, okay? So they're all there. You've got M numbers for Messier objects. You can see, for example, CR for Colander. You can see some stars in here, Epsilon Lyrae down at number 63. But there's a few kind of different types of object in here. The only complicating factor for Northumberland is that obviously, right, you know, we're coming to the end of the summer period in Northumberland. And in the summer, it really doesn't get that dark, even at midnight. So some of the fainter objects, you might have to wait until like the tail end of July, or try to get them, you know, towards the end of May. But even in the middle of summer, you can get the brightest of these objects, even when it's not completely dark. So there you go, 75 objects. That's what I was talking about there. So this is kind of like a picture of how day and night vary throughout the year in Northumberland. So you can see kind of like the dark greys are the brilliant times where we have perfect astronomical darkness. So we're coming to the end of the period where we have all night twilight. So, you know, we're going to be able to do proper darkness from, I think it's August the 5th in Northumberland. Like I said, the spreadsheet is online, so there's the link to it. This PDF will be online as well. Okay, so I'll pop this presentation up on the website at that address as well. I think I've updated it, so I'll put the new version up at the end of this talk sometime. Right, so I've differentiated by difficulty. This is in some respects subjective. Okay, what I think of as being easy, you might completely disagree with. Okay, hopefully not. Easy means generally it's bright, okay, or big and bright. Sometimes big doesn't mean easy. You can have something which is big and faint as well. Okay, so I've tried to make easy, big and bright. The rest, it's kind of my judgment a little bit, but you can take 1, 2, 3, 4 to be a scale of decreasing brightness in some respects. I think I did so there's a points total in this as well. So if you do all 75 objects, you score 150 points. Okay, I was more competitive back in 2003, I think. Anyway, let's go to what some of these things mean in here. So, for example, in the spreadsheet, if you take a look at the size column, okay, second from the right, there's different numbers in here. Okay, so you can see there's, for example, on number 55, colander 359, 4 degrees across. Okay, 4 degrees in size. The one above it, 29 apostrophe. What does that mean? Well, it turns out it means arc minutes. So I want to tell you a little bit about what that means as well, how astronomers measure size in the sky. So when we're talking about how big things look in the sky, we don't talk about like the physical size. It doesn't make sense to talk about the moon as being, wow, look at the moon. The moon is 2,000 miles across tonight. Or look at the Andromeda Galaxy. Look at that, 200,000 light years across. Does that mean it like fills half the sky? Does it mean you need a telescope to see it? We talk about angles when we want to measure distance in the sky. So the picture is really the thing I want you to take away from this. Everything in the sky makes an angle. Okay, so if you think about the top of the moon to the bottom of the moon, it makes an angle of about half a degree, 0.5 degrees. So how big is that? Well, it means like if you hold your little finger at arm's length, you can cover the moon because the angular size of your little finger at arm's length is the same as the angle that the moon makes in the sky as well. So just to kind of like give you some pictures of kind of what angles mean, all of these are not only pictures of my hand, but pictures of my hand held at arm's length. So if you do that with your hand at arm's length, it will make a size of about 15 degrees in the sky, okay? So you can imagine like that's about the size of the constellation Cassiopeia from tip to tip of those stars. So smaller angles, well, your fist makes an angle of about 10 degrees in the sky. You could hold a few fingers up, that would be 5 degrees. So that's about the distance between the 2 pointer stars in the Plough constellation. So when I mentioned that star cluster was about like 5-6 degrees across, you've now got an idea of how big that will look in the sky, because you can simply hold your fingers up like that at arm's length. And that's how big this thing is in the sky. Okay, so these are not like exact, obviously, but I'm guessing my body is in roughly proportion to everybody else's body for this. But even if it isn't, it's not going to make that much of a difference. Now, your little finger measures half a degree. So half a degree is actually the angular size of the moon. The moon is a little bit smaller in the sky than the Pleiades. So if you hold your finger up to the Pleiades will let you be able to see the Pleiades around your finger, okay? The Andromeda Galaxy is a few degrees across, okay? So these are meant to give you an idea of how big those objects are in that spreadsheet. I'll go back to it now. So you have a look down the list, and anything with kind of like degrees. So there's something called the funnel cloud, number 69. 15 degrees by 5 degrees. Well, you get the idea now that that's quite a big thing in the sky. It's quite a big dark cloud in the Milky Way. Go back through here. We've got number 40, Coma star cluster, 2 degrees. So that's kind of like as big as like two or three fingers held at arm's length. So quite big objects in the sky. So it's easy to work these things out if you've got a kind of rough idea of size. For really small angles, 1 degree, so you imagine 2 fingers, that could be like 1 degree at arm's length. 1 degree is split into 60 arc minutes. So that's what the little apostrophe thing looks like. So the moon is about 30 arc minutes, okay? This picture is a picture of the crescent moon and Venus. Venus is about 1 arc minute, and 1 arc minute splits into 60 arc seconds. I think none of the objects on the list are as small as 1 arc minute. Okay, I've tried to keep things bigger and easier than that, but I just thought I would mention it anyway, because Jupiter and Saturn are in the sky at this time of the year, and you might be interested to know that Jupiter's around about 47 arc seconds at the moment. Saturn, with its rings, is around about the same size. The planets are all tiny, which is why you need telescopes to be able to see them in detail at all. Okay, so hopefully that explains the size aspect of some of those objects. Now, the other bit of it is to do with the coordinates, and I'm not going to go into a lot of detail about this, but every object in the sky can be specified using coordinates. And the analogy would be like if you were on Earth, the system you use to specify your position is latitude and longitude. Okay, an equivalent exists in the sky as well. So instead of latitude, stars are measured from the equator in the sky using declination. Okay, so if you were at the North Pole of the Earth, directly above your head would be the North Pole of the sky. For this to work, you've got to picture yourself being kind of like on the top of a sphere or a globe, okay, for this to work. So right above your head is 90 degrees declination. If you go to the equator, right above your head is 0 degrees declination. And if you go to the South Pole, right above your head would be minus 90 degrees declination, okay? So at Northumberland latitude, right above your head is 55 degrees declination because we're 55 degrees north on the Earth. Now, the equivalent of longitude in the sky is right ascension. I'm not going to get into how to do this, okay? But it basically, in the same way that longitude is measured from the Greenwich meridian on Earth, right ascension is measured from an equivalent line in the sky, okay, called the first point of Aries, okay? It's not really important to know because you don't need binoculars for this to work. But if you want to look stuff up on your telescope as well, and you can't find the catalog number, you might be able to find out how to get to it using right ascension and declination. Okay, so anyway, there's a picture of how it works. So you've got the Earth in the middle, right above your head you've got the celestial North Pole. Parallel with the Earth's equator, you've got the celestial equator. So if you're north of that, you've got positive declination. If you're south of that, you've got negative declination. And that's kind of a picture, if you stood facing due north in Northumberland, how the system works. So the pole star, Polaris, sits almost at 90 degrees declination. And you can see there's a kind of concentric circles which mark out hours of right ascension. Okay, right ascension and declination. If anybody really wants to get into that, I can do that at the end of the talk. Okay, and I can show you kind of on Stellarium as well how that works, but it's not really essential other than to explain what a couple of the columns are in that spreadsheet. And just while we're on the subject of position, a much nicer one to use, I think, is the horizon coordinates, where we talk about altitude and azimuth. Now, you can use programs like Stellarium to give you the altitude and azimuth of whatever object you want to look at. And this is kind of like useful because it tells you kind of like how far around from north to face. Okay, so that third picture, if you face north, that's azimuth 0. If you face east, that's 90, south 180, west 270, and back to north at 360. Okay, so azimuth is like a compass bearing. Altitude is how high the object is above the horizon at the time. Okay, so for example, if something is 90 degrees, that's right above your head. If it's 0 degrees, it's flat on the horizon. So halfway up the sky, 45 degrees, half of 90. So you could look up, for example, where this star cluster is at 9 o'clock tonight on Stellarium, and it would tell you maybe it's like 80 degrees, so that's nearly east, and it's 50 degrees, so that's a bit more than halfway up the sky. So you can get coordinates and like aim your binoculars there, and that's one way to kind of trace out where these things are in the sky. The disadvantage with these coordinates is that as the Earth turns, the coordinates will change. Okay, so if you're looking out half an hour later, those coordinates won't work. So it's very specific. You've got to plan ahead if you're going to do this system. I want to tell you a little bit about the brightness scale that we use, and I'm sure this is familiar to some of you, but the system we use is hated by astronomers, professional astronomers. I've got to tell you, there's nothing more a professional astronomer likes to do than gripe about how the magnitude system works, because it's a logarithmic scale. And converting from a magnitude to a number of photons is not a trivial thing for an astronomer to do in their calculations, okay? So when I was doing my MSc in astrophysics, The professional astronomers taught us how to do this, and then just complained relentlessly about the system they were teaching us. But astronomers are really resistant to change. I mean, this has been around for like 2,000 years now. They're not going to change it in the foreseeable future. But as amateur astronomers, it kind of makes sort of intuitive sense if you learn it the way Hipparchus learned it, okay? So the brightest stars in the sky are magnitude 1. The faintest stars he could see with his eyes are magnitude 6. Everything else is somewhere in between, okay? If you keep that in mind, it makes sense, okay? However, the complicated thing about this system is that it's not really precise. Looking at something with your eyes does not tell you the full story about how bright something is. For example, Betelgeuse, the star which is constantly going to go supernova if you're online on Twitter or Facebook. Betelgeuse has a magnitude of about 1. Okay, it's one of the brightest stars you can see in the sky. Okay, if you were to look at it with an infrared filter, it would be one of the brightest, if not the brightest star in the night sky. If you had infrared vision, it would be much brighter than magnitude 1. How on earth do you accommodate brighter than magnitude 1 on this scale? Well, you have to say, well, you got 1, 2, 3, 4, 5, 6. So if it's brighter than 1, it must be 0. It's like even brighter than 1, so 0. What if it's brighter than 0? Well, you're into negative numbers. So the scale needs to be extended because astronomers these days don't just measure things with their eyes, they measure them with all kinds of filters. And also, Hipparchus didn't have a telescope. And we can see things which are fainter than the faintest objects you can see with your eyes. So we've got to naturally extend this scale to accommodate those changes. So this is kind of a picture of how the scale works. So just have a look at the top kind of band here. So instead of going from 1 to 6 now, it accommodates negative magnitudes. So if something's brighter than magnitude 1, it's magnitude 0. Magnitude -1, -2. Astronomers kind of like managed to move things around because they wanted to have like the temperature scale a 0 point, okay? The 0 point of the temperature scale in Celsius is like the freezing point of water. So you've got a 0 for the freezing point of water. For the magnitude scale, astronomers settled on a really stable star which didn't change its brightness, and it's called Vega. So Vega was given magnitude 0. So if it's brighter than Vega, it has to have a negative magnitude. The bottom panel is listing magnitudes which go way beyond the brightness of the stars. So things which are much brighter than the stars, for example, Venus or the full moon or even the sun, they sit with very, very negative magnitudes. The Hubble Space Telescope can see way down to magnitude 30. Okay, Pluto at magnitude 14. You can see there's a lot of objects on this scale. So this scale kind of extends from -30 to +30. So if we kind of go back to the list, okay, I'll really zip back really quick to the spreadsheet here. Look at the third column from the right. You'll see that there's a list of magnitudes here. So the naked eye limit is around about magnitude 6. So if something's at magnitude 6, it's going to be difficult to see with your eyes. But if it's brighter than 6, so that means +5, +4, +3, that should be easier to see. If it's +7, +8, +9, that's going to be correspondingly difficult to see. So that's kind of how that column works. Now, everything I've described about magnitudes refers to star brightness, and stars are points of light, okay? But many of these things in the list are not points of light. They're actually extended objects like galaxies and star clusters. So the magnitude in that list is actually a little bit different. It refers to what we call the integrated magnitude. So let me just give you an idea of how that works. For example, there might be a star cluster with a magnitude of like 6. And what that means is if you collected all the light, you crushed it all together into a single point of light, all of the light of that star cluster would be equivalent to a magnitude 6 star. Okay, so when you look at that list of objects, if it says magnitude 6, but it's got a certain size, maybe it's as big as the moon, you've got to think, well, that's, you can imagine like a star as faint as you can see with your eyes, but then you've got to spread that light out over a big area, which means it's going to dilute how bright it really is. So these are things that you kind of have to accommodate as well. But I've tried to build that into the difficulty rating for the system as well. So in difficult, you might be looking at something and says, well, it's like magnitude 5, but it's rated as really difficult. And that's probably because its light is spread out and diluted over a big area like that. Okay, so that's kind of what it means, the magnitude in that list. Now, how deep you can see will depend on your eyesight and what you're using to look at these objects with. So for binoculars, you can generally see down to about magnitude 9 if you've got relatively good eyesight and all other things are equal, like the moon isn't out, okay? It's not twilight, it's a perfectly dark sky. There are no clouds, no haze. Anything which might affect the visibility, take it out of the equation, and what you're left with are these limits, okay? So these are kind of theoretical limits, and I've got telescope stuff in here as well, because there's no reason why you can't track down these objects with a telescope too. You can see visually, for example, the observatory telescope at Hawksley can take you down to 15th magnitude, okay? So nothing on the list is that difficult. All of this stuff is accessible with binoculars. Okay, now the objects themselves, let me just briefly go through the kind of things you might look for. We have open clusters. So there's a picture of M39, which is number 71 on the list. So this is an open cluster. Now, if you look at the picture, you can see just like thousands of stars, okay? And what I'm talking about when I refer to M39 is the kind of bright grouping of stars that you can see in that picture, the brighter ones there. They form a kind of irregular looking group in amongst the background Milky Way stars, okay? Now, an open cluster tends to contain between like dozens to hundreds, or perhaps in the biggest cases, thousands or several thousands of stars, okay? So there are quite a few of these things in the NB75 list. And they're scattered across the sky, but they tend to occur near the Milky Way. Okay, now the Milky Way is kind of, I'm sure you've seen pictures of the Milky Way either in the sky, you know, like in terms of a photograph in the sky, or like a rendition of it, you know, seen from above where it's a spiral galaxy. In either case, it is a thin disk, and these clusters occur within the disk of the Milky Way, within the plane of the Milky Way. And because we in the solar system are also in the Milky Way, whichever direction we look out along the Milky Way, we will see open clusters in those directions. So open clusters tend to occur near the Milky Way, not far from it. Open clusters are really interesting because they've formed together out of a nebula at roughly the same time. And as the cluster gets older, the most massive stars, they age more quickly. So the massive stars kind of burn through their hydrogen more quickly. So the biggest ones will explode as a supernova. And as you go through time, over the life of the cluster, you lose the more massive stars first. So when astronomers study these, what they do is they look for the red giant stars that are left over, because the red giant stars are the most massive stars in the star cluster, and you can use the age of those red giant stars to date the age of the entire cluster itself. So it's a really important method for astronomers, that. So they look for red giants. Usually a star cluster will contain a few, okay? And some of them are just in the process of turning into a red giant. And this is no exception. So in here, you'll see some orange stars mixed in with them if you look carefully enough. In the NB75, I've also included some interesting stars. Okay, so I've got a few double stars in here and a few variable stars in here as well. Double stars are basically what they sound like. They're two stars close together. Okay, now you can have either a binary system where the two stars genuinely are connected to each other and they're orbiting around each other, or you can have one star here and another star like way behind it so that it looks the same distance to us. Okay, it looks like one star next to another star, but really they're separated by many light years. Okay, so they're both kinds are in the list. Variable stars, these are stars which change their brightness over time. So they're either pulsating or another star is passing in front of them to eclipse their light. Okay, so I've got examples of these in the list as well. Let's move on to globular clusters. So this is the one everybody looks at. It's the most famous one. It's M13, which is number 49 on the list. As you can see in the picture, it's just a ball of stars. And most of the stars in clusters like this are now the mass of the sun or less. And they can contain hundreds of thousands or even millions of stars in some cases. And unlike the open clusters, these tend to have the same ball-like appearance. And also, they're not confined to the Milky Way itself, like the disk. You can find these above and below the Milky Way in all directions, scattered all around in a big halo surrounding the center of the Milky Way. So they tend to be much further away as well. You know, some of these are like tens of thousands of light years away. The best views are going to be through telescopes, but the brightest globular clusters are also visible through binoculars as well. I've got a few bright nebulas in the list. So these are regions usually of star birth or star death. Okay, so the picture that you can see here is of a couple of nebulas which are visible at this time of the year. We've got M8, which is the Lagoon Nebula, and M20, which is the Trifid Nebula. So these are in the constellation Sagittarius. And these are kind of at the low limit of what you can see from Northumberland. I have seen both of these with binoculars from Ingram a few years ago. So even though there's like lots of hills there, there's a nice place just past Ingram where you can drive on a very narrow track, and it's about a mile past the village of Ingram. And there's a nice spot right next to the river where you can park, and the valley kind of like cuts down like that. And in the middle of the valley, you're looking south, and it's a brilliant view of the Milky Way in September, October time. So that's when I saw it from there. Anyway, these tend to be hot gas, so generally heated up by stars inside them to the point where the hydrogen begins to fluoresce, and sometimes they get hot enough for the helium inside them to glow as well. Or they're regions of star death, where a star has maybe blown itself apart, or in any case, a vast injection of energy into the gas has occurred, and the gas is now so hot it's fluorescing as well. So star birth and star death tend to be nebulas. The Orion Nebula is obviously one of the ones on the list, and that's a stellar nursery where stars are being formed. Move on. Okay, so I've got some nice asterisms. So when you kind of like get familiar with the stars in the night sky, you probably know that there are constellations up there. So for example, I've mentioned Cassiopeia, which is a kind of W-shaped constellation. So the way you join the dots makes a W. But in amongst that, because kind of astronomy has developed over thousands of years and lots of different cultures and so on, everybody joins the dots in different ways, and some of these ways of joining the dots are not kind of like formally recognized by the International Astronomical Union. So we have quite a number of asterisms up there as well. These are kind of informal patterns which people know about. So for example, the plough is a really famous asterism, not a constellation. So the plough forms part of the Ursa Major constellation, a much more extensive group of stars, but most people are familiar with the 7 kind of bright stars in the plough. So that's an asterism. There are lots of others up there as well. So the Square of Pegasus is one. The picture you can see, number 11 on my list, was actually popularized about 20 years ago by a Franciscan monk, Brother Campbell. Okay, I think he was called. So Campbell's Cascade is a kind of beautiful chain of stars visible through binoculars. And the idea is that if you use your imagination, it's not hard to visualize this as a waterfall. In the picture, it's kind of on its side, but if you rotate it, it becomes a waterfall of stars splashing down into an open cluster that you can see kind of on the right there, which is NGC 1502. So through the best view of this is through binoculars. Telescopes tend to give you only a view of a very small part of it. So asterisms are really pretty things to look for. And you know what? There are more waiting to be discovered. You might just be randomly looking through the sky and see a pattern that no one has seen before. Okay, let me know if you do. A planetary nebula is on the list as well. This is quite a tough one. This is the Dumbbell Nebula. This is an example of star death. In the middle of that picture is the core of a star which died. Okay, so stars like the sun, when they run out of fuel, their core collapses because the gravity can't, the outward push of the hydrogen burning can't support the star anymore, so it collapses. That heats the star up and it begins a new round of burning of hydrogen and helium, and that new increased phase of burning blows off the outer layers of the star completely. So what you're left with in the center is a hot, dense white dwarf star surrounded by this expanding shell of hot gas containing hydrogen and helium mostly, but also carbon, nitrogen, and oxygen. So the Dumbbell Nebula is on the list, and the picture that you can see there was taken through my telescope, but it's quite a big object. It's about a quarter of the diameter of the full moon. So it's definitely doable with binoculars, but you've got to be looking in the right place to see it. Okay, so once you've seen it, you'll see it easily. But the first time you look for it, it might be a bit of a challenge to pick out. It's in a really rich part of the Milky Way. In amongst the list as well, we've got star clouds and dark nebula. So from a dark site, you can see the Milky Way stretching across the sky during the autumn months. And if you look carefully at the Milky Way, you get these kind of like regions which are a little bit darker than usual. So I'll just highlight a couple here if I can annotate it. Switch the pen on. So this is one of them, I think, around here. I've drawn a blue circle around it. That's the Northern Coal Sack, it's called. There is a Southern Coal Sack near the constellation Crux, the Southern Cross. So it's pretty prominent, and it's near a bright star called Deneb, which is one of the bright stars in the Summer Triangle. So you go out, you look up, you find Deneb in the Summer Triangle, and you notice the Milky Way, and you see there's a dark region there. It looks like there's no stars shining there, but really it's that. What this is actually just dust from all of these stars that have lived their lives and died and blown off their outer layers. In their outer layers are particles of soot or carbon, which is blocking out the light from the more distant reaches of the Milky Way. Let's move on. I've got a few galaxies in there as well. So the brightest is the Andromeda Galaxy, which is best viewed with binoculars, but also I've got M81, 82, which you can see in the picture there. They're visible all through the year. So you can go out any clear night really and try to track those two down. So these are distant versions of the Milky Way. So M81, 82, you can see M81 on the right, which is clearly a spiral galaxy. It's about 12 million light years away, and it contains billions of stars. So you can actually see the brightest galaxies with binoculars. That guy, Steve O'Meara, who wrote those books, he lives in Hawaii where conditions are much better, but also he seems to have some kind of superhuman eyesight as well. He claims these are visible with the naked eye. Maybe, not to me, certainly never to me. I think I've only ever had average eyesight when I've had my glasses or contact lenses in. So there you go. That takes you through everything. If you are the kind of person that I used to be, and keep a record of these things, you can record things like the date and time, where you observed it from. You can give feedback to people in the group. You know, I mean, we're all kind of like contactable through the Nastro forum on the website, or you could share it on Facebook if you wanted to. But certainly if you wanted to kind of like share these observations as you make them, I'd love to see them. I'd love to see that people are going through this. And you could also tell us what instrument you used, whether you could see it with the naked eye, or whether you had to use binoculars, or whether you thought I was just off my trolley when I said it was an easy object and you actually needed the telescope to see it. And if you're really brave, you could try to either, you know, draw a picture of it or make a sketch, or if you want to take a picture, you can do that as well. So there you go. That's just to briefly summarize. I came up with a list of 75 objects which are potentially viewable with binoculars from Northumberland throughout the year. I wanted to do this to widen everybody's experience of looking for deep sky objects, so that we don't just get stuck in a rut of looking at the Orion Nebula night after night after night. Okay. I've included a range of objects. Some of the more challenging objects will probably require you to work on your observing skills to try and figure out why you couldn't see a particular object if you didn't spot it. And just to get us talking about visual astronomy as opposed to astrophotography, which we do a lot, maybe too much of at times. And once you've gotten into using and tracking down these things, you can use this as a stepping stone to find other things that are listed in other catalogues that are maybe more challenging to find. So there you go. That's it. I'm going to stop talking at that point.